Okay, I'd like to thank the organizers for asking me to speak today. It's a pleasure. And it's a particular pleasure to talk about Bergman's work because Bergman's been one of my heroes for 50 years now. I'm going to start out talking about joint work with Marco Peloso. We've been studying the Bergman kernel and worm domain for some time now. And I'd like to report on some of our results. And then after that, I'll talk about some joint work that Marco and I have done with Caterina Stepato. So I'll begin by reminding you about the worm domain. So let R be a positive number, let I sub R be the symmetric interval of radius R about the origin, and let beta be greater than pi over 2. The worm is the domain capital script W, which is a set of all Z1, Z2 in complex 2 space, so that the modulus of Z1 minus eta I log Z2 mod Z2 squared is less than 1 minus eta of log mod Z2 squared. Now here eta is a function whose graph looks like a cup. It's non-negative, it's even, it's convex. It takes the value 0 on an interval centered at the origin. There is a positive number a so that eta x is bigger than 1 when absolute value of x is greater than a. And eta prime is not 0 when eta x equals 1. So the graph looks like a cup with a flat bottom. And if you look at the definition here of the worm, you have to learn how to read these things. You think of this expression as the center of a disk, and this is the element of the disk, and this, of course, is the radius of the disk. And notice that when log Z2 squared is small, then eta is 0, so this is just 1 over here. And notice that the centers are spinning around. And so the shape that you get of this domain is like a worm. And that's where the name worm comes from. There's other versions of the worm that we will look at. The worm that I just showed you is the one that everybody wants to study. It's the one that Diedrich and Fornes created in 1976 or 7. And it has many, many important geometric properties, but unfortunately, it's very hard to study. So there's a lot of substitute worms. Here is the so-called truncated worm, where you can see that it's simplified because the radius is always 1 here, and the modulus of log Z2 squared is chopped off at beta. And there's also the unbounded worm here. You can see it's easy to see that this is unbounded because this condition can be satisfied for very large Z1 and very large Z2. So I've already explained this screen to you about the shape of the worm. So the worm was the first example of a smoothly bounded pseudo-convex domain without a Stein neighborhood basis. What does that mean? Well, it's a fact going back to the 1930s, I guess, that any pseudo-convex domain can be exhausted by smoothly bounded strongly pseudo-convex domains. So the question that arose from that is whether any smoothly bounded pseudo-convex domain has closure that can be written as the decreasing intersection of smoothly bounded pseudo-convex domains. So that's like a dual assertion. And the worm gives a negative answer to this question. And this trumps the earlier known example, which is quite old, of the Hartog's triangle, which also does not have a Stein neighborhood basis, but the Hartog's triangle does not have smooth boundary. In fact, its boundary is not even a manifold. There's a long list of complex geometric properties that the worm has, all counterexamples to important questions from several variable function theory, but I won't take the time right now to go into all those because they're not relevant to what I want to talk about today. I'll just mention perhaps the most profound result about the worm, which is due to Mike Christ. He showed that condition R fails on the worm. That is to say, the Bergman projection does not map smooth functions on the closure of the worm to smooth functions on the closure of the worm. And condition R is important in the study of the boundary behavior of biholomorphic mappings. It's an idea that's due to Steve Bell. Now, Marco's and my goal was to do harmonic analysis on the worm. In particular, we wanted to study mapping properties of the Bergman projection on the worm. And as I already indicated, it turns out that problem is too hard. The worm doesn't have enough symmetry that we could get a handle on anything. And if you want to do, I mean, if you think about the way Fourier analysis developed from the time of Fourier, it always exploited a group. It always exploited symmetry, and the worm doesn't have any symmetry. We cannot even write down a complete orthonormal basis for the Bergman space on the worm. That question seems to be equivalent to an open Munz-Sass type problem. You remember the Munz-Sass theorem is a theorem about monomials being dense in the continuous functions. So we instead studied some substitute worms that were created by Christer Kieselman. These substitute worms do not have smooth boundary, and they are unbounded. But David Barrett has shown the results on the substitute worms can be transferred to the original smooth worm by an exhaustion procedure. And we actually do that, as you will see. So here are the substitute worms. There are two of them. D sub beta is the set of all zeta 1, zeta 2 in complex 2 space, so that the real part of zeta 1 e to the minus I log mod zeta 2 squared is positive, and the absolute value of the log of mod zeta 2 squared is less than beta minus pi over 2. And d beta prime is a set of all z1, z2 in complex 2 space, so that the imaginary part of z1 minus log mod z2 squared is less than pi over 2. And the absolute value of log mod z2 squared is less than beta minus pi over 2. So you can see these two definitions are not terribly different. And in fact, d beta and d beta prime are biholomorphic. So from a complex analytic point of view, they're essentially the same domain. The biholomorphism phi from d beta prime to d beta is z1, z2 goes to e to the z1 comma z2, and it's just a simple high school algebra exercise to check that this is a biholomorphic mapping of domains. Now I'm going to state for you 4 or 5 theorems that Marco and I proved, and I'm sorry to say that the first two have very long statements, so you're going to have to be a little bit patient with me here. We have a smooth cutoff function chi1, and chi2 is 1 minus chi1, and beta, which beta measures the rate of twisting of the worm. Beta is bigger than pi, and nu sub beta is pi divided by 2 beta minus pi. And h is a fixed positive number greater than nu beta and less than the minimum of 1 and 2 comma nu beta. And now we have functions f1 through f8 and f1 tilde through f8 tilde, homomorphic at z and ihomomorphic at w, varying in the neighborhood of d beta prime. That's one of the alternative worms that I defined a few moments ago, and having a certain size condition on the functions and all their derivatives. And we have more functions e and e tilde, so that the derivatives of e and e tilde have a natural sort of bound. And now we claim, oops, what happened here? Okay, so we have functions f1 through f8 and f1 tilde through f8 tilde, satisfying size conditions, and e and e tilde, and they and their derivatives satisfy size conditions. And then we define a new function k sub b in terms of the f's, and there are 8 terms, as you can see, plus an error term. And we also get a function k sub b tilde using f1 tilde through f8 tilde and an error term e tilde. And now we come to the punchline finally. There exist functions phi1 through and phi2 entire and z and w conjugate, which satisfy a certain size condition, so that the Bergman kernel of d beta prime, that was one of our alternative worms, admits the asymptotic expansion. So this is the whole point of this theorem, is that we have an asymptotic expansion for this alternative worm d beta prime, and here's what it looks like. And what you notice about this, when you study a formula like this, what you should look at is the singularity, because the singularity, of course, is crucial for the mapping properties of the Bergman kernel. And what you see is that it's isotropic in the C1 variable, and non-isotropic in the Z2 variable. And when you have mixed isotropies like that, things get complicated. And you can imagine, if you know a little bit about the Bergman kernel, that since d beta and d beta prime are biholomorphic, we could use this asymptotic expansion for the Bergman kernel of d beta prime to derive an asymptotic expansion for the Bergman kernel of d beta. That's what we're going to do in the next theorem, actually. So here's the next theorem, and I'm sad to say this theorem also has a rather long statement. Now we're going to have functions g1 through g8, g1 tilde through g8 tilde, and also functions little g1 and little g2, and the derivatives of the kappa of the g's satisfy a size condition. And as before, there are functions e and e tilde satisfying a certain size condition. And instead of having k sub b, now we have h sub b, which is going to be a tool in getting the asymptotic expansion. And here it comes. So we have an asymptotic expansion for the Bergman kernel of d beta, and it looks like this, and it goes on 2 screens. And you'll see that the singularities now are of a different nature, but once again, they're isotropic in the 1 variable and non-isotropic in the 2 variable. And I should emphasize here that everything I say about the worm is going to be about the classical worm in dimension 2. It's a current matter of study to understand worms in higher dimensions. Marco and I and Katerina are studying this. David Barrett and his collaborators have been studying it. But there's still a lot to learn about higher dimensional worms. So everything I'm going to say today is going to be about 2-dimensional worms. So now we're going to have some theorems that you can state in just a few words. And these theorems are really the point. Let's P denote the Bergman projection on the domain D sub beta, then P maps LP of D beta to LP of D beta only for this range of P. P is greater than 2 divided by 1 plus nu beta, and less than 2 divided by 1 minus nu beta. And this is kind of a remarkable result because, after all, P is a canonical kernel. And traditionally, we're used to the idea that canonical kernels map LP to LP for all values of P strictly between 1 and infinity. But for the worm, things are different. Only this range of P is sharp. So only for this range of P do we get LP boundedness. And the fourth theorem, which is different, is that P prime, which is the Bergman projection on the domain D beta prime, is bounded on LP for all P. So this is a little bit shocking, actually, because D beta and D beta prime are biholomorphic, and the Bergman projection for D beta is only bounded on a restricted range of P, whereas the Bergman projection for D beta prime is bounded on LP for all P. How could that be if these 2 domains are biholomorphic? Well, the answer is that the 2 projections are related by the Jacobian, and the Jacobian is unbounded. And now we're going to use Dave Barrett's idea and derive a result about the original smooth worm by exhausting that smooth worm by these non-smooth approximate worms. And the result now is that the Bergman projection for the original smooth worm is bounded on LP only for this restricted range of P, and that's the restricted range of P that we saw in theorem 3. So this could be considered to be one of Marco's and my main results from our earlier work. So beginning in 2016, Marco Peloso and Katerina Stepato and I started a new collaboration on the worm, and we have a couple of papers in print and some other papers in progress. And among other things, we show that the Bergman projection is not bounded for certain worms. The Bergman projection is not bounded on any Sobolev space and not bounded on any LP except P equal 2. So that's a rather dramatic result. And if we do find a complete orthonormal basis for the Bergman space on D beta prime. And this orthonormal basis that we find is related to a Bose problem. And I'm going to spend most of the rest of the talk telling you something about this work. So let me remind you that the unbounded worm is W infinity, which is a set of all Z1 and Z2 and C2, so that modulus Z1 minus e to the I log mod Z2 squared is less than 1 for Z2 not equal to 0. And we'll summarize here some well-known facts about the domain W sub infinity. It's a pseudo-convex domain, which one checks by just examining the Levy form. The boundary of W omega is smooth, except at points Z1, 0, where mod Z1 is less than or equal to 2. W infinity has non-trivial Nebenhülle, which means that it is not the decreasing intersection of pseudo-convex domains. And the smooth part of the boundary is strongly pseudo-convex except at the points of the critical annulus 0 cross C star. And here C star is the complex plane, take away the origin. Now, our first important result, as indicated above, is this. For all S bigger than 0, the Bergman projection P does not map the Sobolev space WSW into itself, nor does it map LP into itself for any P other than 2. So we point out that this domain that we're studying is unbounded and non-smooth. However, and this is an important point, the analysis of the singularities of the Bergman kernel shows that the irregularity of the projection is caused by the pathological behavior of the kernel near each point of the critical annulus A, where the boundary of the domain is actually smooth. So it's not the non-smoothness of the boundary that's causing these mapping properties. It's something more subtle. We cannot provide much of the details of the proofs, but we'll just say we exploit tricks that date back to Dave Barrett for reducing the problem to issues of one complex variable. So I'll say a few words about that. So for convenience, we will denote W sub beta by W, and notice that W is the union over Z2 in C star, which is C take away the origin, of the disk with center e to the I log mod Z2 squared and radius 1 cross singleton Z2. And that's easy to see from the definitions. We're going to define L of Z to be the log of Z1 e to the minus I log Z2 squared plus I log Z2 squared, and U to be the set of all U plus IV W2 in complex 2 space with V bigger than 0 and absolute value U minus log mod W2 squared less than arc cosine e to the minus V for W2 not equal to 0. And finally, we will let omega denote either W the worm or U, which I just wrote down for you. And we have that the Bergman space of A2 of omega, where omega is either W or U, decomposes as the direct sub of Hj of omega, and this is a key idea of Barrett, and this is really central to our work here. Hj of omega is the set of all f in the Bergman space of omega, that is to say the square integrable holomorphic functions, so that you have this rotational invariance property in the second variable. And you could write it two different ways. You could write it like this, or you could write it like this. So this is Fourier analytic in spirit, as you can see. And each HAW is it's easy to see. Each HAW is non-trivial, and there's an isometric isomorphism capital T from Hj of W to Hj of U. And we sort of think of U as an unwound version of the worm. So in his famous ACTA paper, Dave Barrett analyzes the space H-1. We, on the other hand, have to analyze all of the HJs. So our work is somewhat more ambitious. So we define phi of Z to be minus I times L of Z, which is a function I defined a couple of screens ago, adjusted by log 2. comma Z2. U as before is this. U is pseudoconvex. Phi from W to U is a biholomorphism. And A2 of U, it turns out, is infinite dimensional. Now we're going to define alpha J of U plus IV to be a constant times the hyperbolic sine of J plus 1 arc cosine e to the minus V, and capital Kj to be 1 over 2 pi integral 0 to infinity e to the I Z minus W conjugate C divided by alpha hat minus W I C dC. And now we have the Bergman kernel of U. Remember, U is sort of the unwound version of the worm. And its Bergman kernel is 1 over Z2W2 conjugate, summation over J and the integers, K sub J of Z1 ZW1, where K with J was defined here, times e to the minus 1/2 Z1 plus W1 conjugate, Z2W2 conjugate, to the J plus 1 power. So it's always nice when you could decompose your Bergman kernel into fundamental pieces like this. And here's a theorem. The kernel function K sub U extends holomorphically in C and anti-holomorphically in W. Near each point in U closure, cross U closure, take away sigma, where sigma, as usual, is the boundary diagonal. And 2, there exists a holomorphic function G from U cross U to the complex numbers, so that K sub U, the Bergman kernel, is equal to G divided by Z2W2 conjugate times Z1 times minus W1 conjugate squared. So this is nice because it's a much easier to understand formula for the Bergman kernel. Also, there's a function little g on this annulus, so that capital G stays bounded as either Z1 or W1 tends to infinity. If Z1 minus W1 conjugate tends to infinity inside of the half plane, and if this expression e to the minus 1/2 Z1 plus W1 conjugate Z2 W2 conjugate tends to zeta in A, where A is there, then capital G of Z tends to little g, and little g minus this complicated expression extends holomorphically to a neighborhood of A closure. As a consequence, the Bergman kernel tends to 0 near each point ZW or WZ, with Z1 equal infinity, Z2 is in C star union infinity, and W is in U. Now we have this lemma. Here's capital L of Z again. We've seen it a couple of times before. This defines a complex valued holomorphic function in the variable Z on the domain capital script D, which is the union over Z2 and C star of e to the I log mod Z2 squared H cross singleton Z2. And the same is true for E sub eta of Z, which is e to the eta LZ, where LZ, of course, is right up here. And now we have a statement about the Bergman kernel of W. And it is that the Bergman kernel looks like Z1W conjugate, Z2W conjugate reciprocal. We've seen this before. Summation of the KJs applied to little l of ZL of W. And then these expressions in the capital E's, which you saw defined just a few moments ago. In particular, when Z comma W is in this product domain, the kernel function takes this form. So this is just writing out more carefully what the kernel function looks like. Last of all, we have that the Bergman kernel K of A2W extends holomorphically in Z and anti-holomorphic in W near each point CW of the boundary of W cross W, except when Z1 is 0 or W1 is 0, when Z2 is 0 or W2 is 0, or when for some R at 0, 2, we have Z1 has this form R e to the I log mod Z2 squared plus or minus R cosine R over 2, and W1 has a similar form, and the logarithms of Z2 squared and W2 squared are bounded above. For case 1, we notice that there exists a holomorphic function H from W cross W to the complex numbers, with the Bergman kernel having this form, and a holomorphic function little g on A. We've seen this g and A before, so that H stays bounded as either Z1 or W1 tends to 0. If Z1 tends to 0 or W1 tends to 0, and if the E's times W2 tend to zeta, then H tends to G, and G minus this complicated expression extends holomorphically to a neighborhood of A closure. We've seen something like this a few screens ago. As a consequence, K is singular at all points CW of the boundary with C1 is 0, Z2 is 0, or W1 is 0, W2 is 0. And of course, that doesn't come as any surprise because you see these expressions right here. Now we'll pass to the next paper by Krantz, Peloso, and Stapato. And for the reader's convenience, we'll recall a few definitions. These are very well known. I hope you could just be patient with me for a minute. We have a sequence of vectors Vn and a Banach space capital V, a Schauder basis for each W and V. This is a Schauder basis if for each W and V there is a unique scalar sequence Cn. So the summation Cn Vn converges to W with respect to the norm topology. That's a Schauder basis. If H is a separable Hilbert space, then a sequence Hn in H is an orthogonal system of Hn inter product is 0 and m is not equal to n. It's an orthonormal system if it is orthogonal, and each Hn has modulus equal to 1, or its norm equal to 1. And a complete system if 0 is the only vector that is orthogonal to Hn for every n, or equivalently if the linear span of the Hns is dense in V, or in H. A complete orthonormal system is automatically a Schauder basis, and it is called an orthonormal basis. On the other hand, a sequence in V that is not orthogonal may be complete without being a Schauder basis. In other words, the aforementioned sequence Cn may exist for all W without being unique. In the analysis on the worm domains d beta and d beta prime, a special role is played by the function E eta z is e to the eta Lz, and of course we've seen L and E before. And you see that E eta looks like Z1 e to the minus I log mod Z2 squared to the eta power e to the I eta log mod Z2 squared. The function L is well defined and holomorphic in a domain containing the union over beta of the d beta primes. And moreover, we point out that the fiber of d beta prime over each Z1 and Z02 take away 0 is not connected. So this actually plays a significant role in our analysis, that these fibers, this is because the worm, of course, wiggles. So therefore, these fibers are not connected. And Lz is locally constant in Z2, but we can't say it's constant just because the fibers are not connected. The same happens with E eta. For eta and C take away these integers, while Ek of Z, which is Z1 to the K for all K and Z and d beta prime. Hence, the functions E eta are the analytic continuation to d beta prime of the monomial Z1 to the eta defined at d prime pi over 2 using the principal branch of the log. It is well known that functions that are holomorphic in a neighborhood of the closure of W beta are not dense in the Bergman space. We will state but not prove the following. If beta is bigger than 2 pi and A2 of W beta closure denotes the closure in A2 of W beta of functions that are holomorphic in the neighborhood of W beta, then if F is an A2 of W beta closure, then F is holomorphic on W beta hat, where W beta hat contains the union over A of the set of all Z1, Z2, so that log mod Z2 squared is bigger than A and less than A plus 2 pi, and modulus C1 minus e to the I A is less than 1. Therefore, A2 of W beta closure is not a subset of A2 of W beta. The same conclusion holds true with W beta prime in place of W beta. And here W beta prime is the set of all Z1, Z2 in complex 2 space, so that modulus Z1 minus e to the I log Z2 squared is less than 1, and log Z2 squared is less than beta. So that's one of our substitute worms. As we see in this definition, we have replaced the smooth function eta with the characteristic function of the complement of the interval minus beta beta. In particular, the polynomials are not dense in either A2W beta or A2W beta prime. And this should be contrasted with the classical result of Catlin that goes back 40 years, where he showed that every smoothly bounded pseudo-convex domain omega that has the property that the holomorphic functions at C infinity of omega closure are dense in A2 of omega. So thus we are led to consider the set of monomials of the form e to the aj, a to j, z, z2 to the j, for j in the integers, and ask whether these are orthogonal and or complete for some choice of values of a to j. And that's going to be our focus for the next several screens. So let dA be the Lebesgue measure in the complex plane. Let real alpha and real beta be bigger than -1. And then the integral over the disk of zeta to the alpha, zeta to the beta conjugate is equal to, not a big surprise, pi times an expression with the gamma function. In particular, zeta to the alpha and zeta to the beta are never orthogonal to each other in A2, because this is never zero. For a given bounded domain omega in C2 that is rotationally invariant in the second variable Z2, such as W beta, the worm, and W beta prime, the truncated worm, using the Fourier expansion in Z2, the Bergman space A2 omega decomposes as an orthogonal sum. And you've seen a version of this before. Like this, I told you this is one of Barrett's key ideas, where F is holomorphic in Z1 and locally constant in mod Z2. And of course, it's only locally constant in mod Z2 because the fibers are not connected. The orthogonal projection of A2 onto HJ is given by this formula right here. That's just Fourier analysis. And we set, therefore, F of Z1 comma mod Z2 equal to Qj of F. Here's Qj of F, divided by Z2 to the J, which makes good sense given the definition of H. And observe that the right-hand side is holomorphic in omega, but depends only on the modulus of Z2. So F is locally constant in mod Z2, and in general, it will be constant only if the fibers over a point in Z1 and Z2 and omega with Z1 fixed is a connected set in the Z2 plane. In general, as I've noted, our fibers are not connected. Let us go back to the case of W mu prime or W beta prime and let FG be an HJ. Capital F can be written as F of Z1 comma mod Z2 times Z2 to the J. Of course, we've seen that before. And G of Z1, Z2 is written similarly. And then we calculate the inner product of F and G in the Bergman space. And you can see the calculation here. You could just, we pass the polar coordinates. We do a standard change of variable, and we end up down here. And as have we seen before, we let nu be pi divided by 2 mu be the reciprocal of the widening number of W beta prime, and let H be the entire function sinh of mu times j plus 1 plus iz divided by j plus 1 plus iz, and define gamma alpha beta to be H of alpha minus beta conjugate. And we have this proposition. Let mu be positive, let alpha be a complex number, j an integer, let f sub alpha j be e sub alpha of z, z2 to the j. Then f sub alpha j is in the Bergman space if and only if the real part of alpha is bigger than -1. Moreover, if real alpha and real beta both are bigger than -1, then the inner product of f alpha j and f beta j is equal to this expression involving the gamma function, just as we saw a few moments ago. Well, I don't know where it went, but anyway. In particular, f alpha j, f beta j is equal to 0 if and only if alpha minus beta conjugate is equal to 2k nu plus I times j plus 1, with k a non-zero integer. So you can imagine proving something like this is just a calculation. And here's the calculation. You can see here writing out the definitions of the E's, and this simplifies to this. And here gamma sub alpha beta is equal to this expression, which calculates to that. And therefore gamma sub alpha beta equals 0, and if and only if mu times j plus 1 plus I alpha minus beta conjugate is an integer multiple of pi I, that is to say alpha minus beta is 2k nu plus I times j plus 1. So when alpha equals beta, this previous calculation gives a formula for the norm of E sub alpha z times z2 to the j, which is finite if and only if the real part of alpha is bigger than minus 1. You can see the real part of alpha right here. This proves the first part of the statement. The second part now follows from the lemma, and the following corollaries follow at once. For the real part of alpha bigger than minus 1, we have f alpha j is in the Bergman space, and f alpha j Bergman norm squared is equal to this expression involving the hyperbolic sign and the gamma functions. Now we'll define h sub lj to be this expression involving our old friend capital E and z2 to the j. And here's an important corollary. For mu bigger than 0, each of the sets h sub 2k comma j for j and z and k equals 0, 1, 2, and h sub 2k plus 1j for j and the integers and k is 0, 1, 2, and so on, is an orthogonal system in the Bergman space. So after a lot of work, you see, we finally have generated an orthogonal system in the Bergman space for one of our worms. In order to establish that the system f alpha j is complete, we are led to consider a Wundt-Sass problem, as I told you before. So let's talk about that for a few moments. If we set delta equal to this disk and consider a set of functions zeta to the lambda k, we would like to find the necessary and sufficient condition for the set to be a complete set in A2 of the disk. That is, its linear span is to be dense in A2 of the disk. So that's the basis of our Wundt-Sass problem. Theorem: let S be the subset of A2 of the disk whose elements are the functions zeta to the lambda k for k equals 0, 1, 2, where lambda k equals ak plus z naught plus ib. A is between 0 and 1, c naught is bigger than minus 1, and b is in R. Then S is a complete set in A2 of the disk. So we'll say a few words about the proof. C from U to the disk is U is the upper half plane, and the biholomorphic mapping from the upper half plane to this particular disk is 2i over I plus W plus omega. And then T maps A2 of the disk to A2 of U, where T is defined by this formula right here. And C, of course, is our Cayley map. And that's a surjective isometry. By the Paley-Wiener theorem, the Fourier transform given by this definition right here provides a surjective isometry of A2 of U, the upper half plane, onto L2 of 0 infinity with respect to the measure dc over c. Therefore, zeta to the lambda k will be complete at A2 of the disk if and only if the Fourier transform of t of zeta to the lambda k is complete in L2 of 0 infinity dc over c. So Fourier analysis has reduced our problem about completeness to studying a fairly standard L2 space. Now, t of zeta to the lambda is equal to this just by a simple calculation. And the Fourier transform of this expression, here's the definition of the Fourier transform, turns out to be this. That's just a straightforward calculation. And therefore, the Fourier transform of t of zeta to the lambda turns out to be this expression. Here, gamma is the standard gamma function. And therefore, the set zeta to the lambda k is complete in A2 of the disk if and only if the set C to the lambda k plus 1 e to the minus c is completed in this L2 space, and that is the set c to the lambda k plus a half e to the minus c over 2 is complete in this L2 space. So now we've reduced the problem to something even simpler, just the simple L2 space with respect to Lebesgue measure. Now we'll consider the transformation c goes to c to the a, which we will call t, and this maps 0 infinity to itself and induces an isometry lambda of L2 0 infinity onto itself, given by lambda of c equals 1 over square root of a psi of t to the 1 over a, t to the 1/2, 1 over a minus 1. Under this transformation, since lambda k is ak plus c naught plus ib, as we saw before, we see that c to the lambda k plus a half e to the minus c over 2 is complete in L2 0 infinity, if and only if t to the k, t to the alpha, e to the minus 1/2, t to the 1 over a is complete in L2 0 infinity, where alpha is c naught plus 1 over a minus a half plus I b over 2a. And we know that the system t to the n plus c to the minus t over 2 with c bigger than minus 1/2 is complete in L2 of 0 infinity. So if psi is L2 of 0 infinity is orthogonal to all the expressions t to the k, t to the alpha, e to the minus 1/2, t to the 1 over a for all k equals 0, 1, 2, it follows that the integral of t to the k plus real alpha e to the minus 2 over 2 conjugate of t to the minus I lm alpha e to the 1/2 t minus t to the 1 over a psi t is 0 for k equals 0, 1, 2, and so on. And since a is between 0 and 1, e to the 1/2 t minus t to the 1 over a is bounded, and also the real part of alpha is bigger than minus 1/2. So we obtain that t to the minus I lm alpha e to the 1/2 t to the minus t to the 1 over a times psi is 0, and therefore, of course, psi is 0. And that completes the proof of this theorem. So we've proved the completeness of this set S in the Bergman space of the disk. From our Munz-Sass result for the Bergman space E2 of the disk, we obtained the following density result in A2 of W mu prime. Let mu be bigger than pi over 2. Let HLJ of Z1, Z2 be as in formula 15, where formula 15 is, let me see, here, right here. Then the HLJs are a complete set in the Bergman space of W mu prime. So this has been sort of the point of all of our hard work for the last 20 minutes. We now have a dense set in A2, and the HLJs are the union of the two sets in the corollary. So our purpose here has been to explore the harmonic analysis properties of the worm, and I think it's pretty clear that we've only established a beginning for this program, and there are many, many open problems left to be considered. Thank you very much for your attention.